Okay, so now it's 12:30. Um, Welcome to the class. I can see we have 11 students today. So this is um, my first time doing an online class at NTU. Um, so let's see. This is going to turn out fine. Okay. So today we will start our last topic in this course. Um, so in this last topic, we will focus on transactions. Okay, transactions. All right. This is also a fascinating topic. Actually, this is really some interesting topic in my opinion. Okay, so we will take our time and we will really enjoy it. Okay, so I'll try to make you understand a lot of issues related to transactions. Okay, all right. So just to get things started, okay, just to get things started. Okay, so a transaction, you can think about a transaction as a program that is running in the database systems. Okay, um, and every such program will have to do um, data accessing. You see what I'm saying? Okay, they will have to access the data in the database. Okay, of course, this is very intuitive, right? Because otherwise, why would you want to run a program in a database system, right? So you want to access data. So everything sounds easy, right? I mean, come on, you have a database system, so you can run programs. Why is it a big deal, right? Well, that's exactly the reason why this topic is interesting. Okay, there will be a lot of big deals, as you will find out. All right. So to give you a very high level idea, why things could go wrong, you could imagine, um, what happens if all these programs they try to compete with each other in accessing the same data. You see what I'm saying? You can imagine, there's just a piece of cake there, but a lot of people, they try to grab the cake, right? And everybody thinks that he or she has already got the cake. But in reality, you could have some very weird situation where only, you know, most of the people end up, having no cakes at all, even though, they think they have got one. Okay, this might sound strange at this point, but at the end of today's lecture, you will understand much better, what I'm talking about. Okay. All right. So now let's get started. Okay. If we want to talk about transactions, we have to talk about this notion of state. Okay, a state. All right, the status. All right, the current status. So formally, this is a scientific course, right? So we should try very hard to make everything in this course as rigorous as possible, right? So when I say state of a database, I want to give it a very formal definition. Okay, so here, look, your database consists of tables, right? Consists of tables. And every table consists of columns, those are the attributes, and also the rows, right? Those are the tuples, right? So you can see tuples have values, right? Every tuple has a value under each attribute, right? So I will refer to that as the content of a table, right? So now, formally, the state of a database, all right, the state of a database is defined as the content of all the tables in the database right now. Okay, so let me repeat. The state of a database is defined as the current content, okay, at this very moment of all the tables that exist in the database. All right, so that is defined as the state, right? So in other words, states can change, right? So every time you change something in any of the tables, and then the state basically um, changes from the previous state to the next state. You see what I'm saying? All right. So that's the notion of state. All right. So this is very important. Okay. Now, the next notion basically tells you why we are interested in, the so-called states. Okay, so once I have already defined the notion of state, and then I can say whether the current state is legal or not. Okay, legal or not. Now, what do I mean by legality here? Well, you should recall that on a database system, on a database, you could impose multiple constraints. Okay, multiple constraints. Now here I am listing some very common constraints for you. For example, you can specify the primary key constraint. Basically, this says, on a certain table, if you say, let's say attribute A is the primary key, and then you should not have two tuples having the same A, right? So for example, A could be some sort of ID, right? So this is the primary key constraint, right? And currently this constraint might be violated. You see what I'm saying? Okay, let's say if you insert a tuple, and this tuple has the same ID as another tuple already in the database, and then this creates a violation of the constraint. Okay, and therefore, I have every right to say whether or not the current state of a database is legal or illegal. You see what I mean? Okay. Of course, primary key constraints, they are not the only type of constraints that can exist in the database. You could have, the so-called foreign key constraint, not null constraints, all right? And you can even, define whatever constraints you want, right? Using this so-called triggers, right? So you can impose any constraint you want, right? So all these constraints will have to be satisfied. Otherwise, the database is in a broken mode, right? A broken state, right? So formally, if the current content of the database, which means that the state, right, the current state of the database, if it satisfies all the imposed constraints, and then we say, this state is legal, the state is consistent, okay, consistent with the constraints, all right? So this is the formal word, okay, consistent. So next time you hear me say, our database is consistent or it's legal, you know exactly what I'm saying, okay? So basically I'm saying, it satisfies all the constraints imposed by the data, imposed on the database by people, okay? So if you think about it, the power of a database system lies in the fact that it's able to enforce all constraints automatically for you. You see what I'm saying? Okay, so it's sort of like a grand guardian of everything. Okay, a grand guardian of everything. All you have to do as a normal user is to specify the constraints. All right, and then you can take for granted that the system is going to enforce those constraints for you 100%. Okay, so if you think about it, that's exactly the power of a database system. All right, so this is not something you can achieve using other, for example, more straightforward and primitive systems such as Excel. You see what I'm saying? Excel. Okay, so that's why database systems are very intricate and very powerful and very elegant systems. Okay, cool. Well, now here comes the protagonist. Okay, the main character of today's show. Okay, and this is also the main character for the next few weeks. Actually, for the rest of the semester. Transaction. Okay, so this big name is coming into the scene. Okay. So what is a transaction? Well, as I mentioned at the very beginning of today's lecture, you can think of a transaction as a program. Okay, as a program. Okay. Now that's why, as you can see the definition here, right? The transaction, okay, is a sequence of instructions, right? A sequence of instructions. Well, that is essentially what a program is, right? you submit a C++ program, a Java program, Python program, whatever, right? So there were a lot of statements there, right? So these statements are meant to be executed one by one. You see what I'm saying? Okay. However, a transactional database is more than just a program, all right? Because there is, if you look at the definition, right, there's another requirement, okay? So this program basically will have to satisfy this all or nothing requirement, okay? All or nothing, okay? So this basically says, you know what, there are only two possible outcomes. So either you execute the entire program completely, okay, entire. So this has to be complete, all right? So the whole program will have to get executed, and the effect of the program will have to be made permanent. Okay, so that's basically saying, the program will have to serve its intended purpose. Okay, so formally, we say the first possible outcome is that the entire program, the entire sequence of instructions will have to be executed in full. Okay, so this is one possible outcome. And the other possible outcome is that none of the instructions should be executed, okay, as if the program or the transaction did not exist in the first place. All right, so this is the all or nothing requirement for the so-called programs. Okay, so these programs, by the database jargon, they are called transactions. Okay, so this is what a transaction is about. All right, so this all or nothing requirement is not easy to enforce. Okay, in fact, this all or nothing requirement is going to create a lot of issues. Okay, when you have multiple transactions running at the same time, they could interfere with each other. Okay, so in the next few weeks, we're going to talk a lot about such kind of interaction, how different transactions can affect each other. All right, but here, this is the first time you hear this requirement. I want it to leave a very deep impression on your minds. Okay, this is the so-called all or nothing requirement. Okay. All right, so here I'm showing you an example. Okay, typically I use a big T to represent a transaction. Okay, so as you can see, these are the instructions of the transaction. You submit these instructions to the database system, right? So these instructions are meant to be executed, in a top-down manner, right? One instruction at a time. Okay. So here in this remark column, by the way, this column is not part of the transaction. Okay, so I'm including this column here just to explain the meaning of each instruction. Okay, so here just read A. So you can think about this A as some particular tuple in some particular table. All right, so for example, it could be from the student table, and this could be the ID of some student that you are interested in. Let's say John. Okay, so this could be John's name, this could be John's GPA, whatever, right? But it's just a single value. This tuple value is very well defined, right? Because you know what a tuple is. All right, if you specify a particular attribute and then you have the value of the tuple on that attribute, right? So as you can see, attribute here. Okay, so such kind of values are stored on disk, right? So these are database systems, right? So these values are stored on disk, right? So by reading this value, so you are bringing this value from the disk to the memory. All right, so this is what this operation is doing. Okay. Now, if you look at the second instruction, right? So this says, all right, now let's increase this value. All right, so this time I want you to think about this A as sort of like salary, okay, of some employee, right? So join. So here we are increasing. Actually, you know what? Salary is not a very good example. Let's say this is the bank account balance. All right, so the balance of some bank account. Let's say John's bank account, right? So this A equals a plus 1 here essentially says, we would like to deposit $1, okay, $1 into this bank account. Okay, so this is like a transaction. You see what I'm saying? Like a banking transaction. All right, but the thing is, you have to understand this is taking place only in the main memory, right? And it doesn't count, right? Because if you unplug the power, and then the memory value will be lost, right? So the database system will have to make it permanent, and the way to do that is to write the new balance back to the disk. You see what I'm saying? Okay, so that's what this write A is doing, right? So this is updating the value of the tuple on disk. Okay. All right, so at this point, it sounds like the disk has been modified, right? And the transaction will have to be complete in the sense that you will have to inform the database system very, very formally that, hey, you know what? I'm about to finish. Please let me finish. This is called committing. Okay, commit a transaction essentially says you want to finish the transaction. You want to declare that all the changes that have been, all the modifications that have been made will need to be made permanent. You see what I'm saying? Okay, so if you are transferring $1, actually here you are depositing $1 into a bank account, and then this effect will have to be made permanent, right? So this is the meaning of all. You see what I'm saying? So this all we have to say the effect will have to be durable, okay? No matter what, all right? So if I commit a transaction, and then I should take for granted that I have indeed deposited $1 into this bank account balance, all right? You cannot tell me, hey, your transaction has committed, but for some reason, we regret to inform you that the bank account has not been credited. Okay, so that kind of situation cannot happen, right? So because this is the all requirement. All right, so the meaning of all. Now let's look at the nothing requirement. Okay, so still the same transaction, as you can see, read A, still the same example as before, right? So we're reading the original balance of some bank account, and then we increase it in memory, and then we write it back to the disk. Okay, so let's say the writing is successful. Okay, so in other words, the value of the bank account has indeed been modified successfully on the disk, right? So the disk has changed. You see what I'm saying? The original value has been updated, right? But the thing is, a system error can occur anytime. You see what I'm saying? Okay, there are so many possible errors. So for example, let me tell you one disastrous error, catastrophic error. Okay, so suppose you accidentally switch off the power. Right? So that will be the most stupid, however, the most catastrophic kind of error that could happen, right? And this is very very real, right? I mean, this could happen. This could really happen, right? I mean, you accidentally switch off the power, or I don't know, maybe there's an earthquake or something like that, right? And the funny thing is that such kind of error happens after the disk has already been modified. You see what I'm saying? All right. So it's not that it's not that the balance has not been updated. It has been updated, but somebody unplugs the power, and therefore the transaction has not committed. You see what I'm saying? The committed, right? It has not committed. You see what I'm saying? So if you go back to the previous example, you can see if a transaction says I'm done, you have to officially declare it. Okay, I am committing myself. So at this moment, and then I know that the transaction is fully executed, right? But here you see, I have not seen this commit statement. All right, so at least this statement has not been executed by the database system, and therefore, from the perspective of the database system, this transaction has failed. all right, has failed. Now, in this case, it needs to be aborted. You see what I'm saying? Aborted, all right? So there are only two possible outcomes for a transaction. Either it is committed, which means it has been successfully executed in full, in which case the effect, the modifications it makes to the database system will have to be ensured, will have to be made permanent, okay, will have to be preserved forever. All right, so this is the first possibility, okay? Or the transaction did not manage to commit. And then in that case, we say that the transaction is aborted. Okay, aborted. Now, for example, here the transaction, some error has occurred, and therefore the transaction needs to be aborted. Okay. However, if you think about the all or nothing requirement, right? So here, this nothing requirement kicks in, right? So if a transaction is aborted, and then we will have to, in database jargon, roll back, okay, roll back all the effects that the database has created on the database system, okay, roll back, okay? So in my little example here, I said, right, so this write A statement has already changed the disk, right, has already modified the disk. And therefore, if since the transaction has been aborted, the database will have to start a rollback process. This is called a recovery process, okay, a rollback process to cancel, okay, to cancel all the modification to the database, okay. So you can be assured that even if somebody unplugs the power anytime, okay, anytime, so database, I mean, this guy is a villain, right? And he or she tries to mess with you, right? So he or she tries to wreak havoc to the database system, right? So this person could unplug the power anytime. You cannot predict it. But the thing is, no matter what happens, such kind of behavior cannot change the legality, the consistency of the database state. All right. So in this case, from the user's point of view, right, the user would have to say, well, since the transaction did not commit, right, according to the all or nothing requirement, there should be no effect left behind by the transaction. You see what I'm saying? Okay, there should be no effect. And therefore, if I ask you, what should be the value of A, okay, the value of this bank account, then you should tell me, definitely it should be the original value of A, okay, as if no transaction ever existed. Okay, so this is the all or nothing requirement. Okay, so I spent a lot of time. If you look at it, right, I've been talking for 20 minutes, and I have intentionally been going very slow on this, right? Because this is the start of everything. You see what I'm saying? This is the foundation of everything. Okay, we will spend the next few weeks talking about transactions, and one very important purpose of our discussion is to implement, is to realize this goal, this objective. All right, this all or nothing objective. All right. If you think about it, this is not a trivial thing to guarantee. Okay. And if you have only one transaction running in a database system, and then it will be relatively easier. Okay. If you have just one at any moment. All right. So it's like a very, very slow system, right? So only one transaction running at all times, right? And then it will be relatively easier. However, the challenge lies in the fact that you might have multiple transactions running at the same time, and these transactions might interfere with each other, okay? And in such scenarios, if you still want to guarantee this all or nothing requirement, it will be much more complicated, okay? And we'll see about this, okay? All right, so I would like to solicit some feedback from you at this point. I cannot see your faces, and I can see we have 26 students here, so that's very close to 20%, because we have 150 students here, right? So it's close to 20%. I do hope you can give me some feedback, all right? So if what I have been talking, what I've been saying so far makes sense to you, please type something in the chat box so that I can know it. Okay, so give me a something so that I can see. Okay, if okay, good, thank you. So I'm looking at a lot of feedback. Okay, wonderful. All right, good, very nice. Thank you. All right, so let's move on. Okay, so let's move on. All right, so now you know a lot of notions already, right? So database state, right? So you already know what that is. And you also know, we want consistent database state, right? We want consistent database state, right? So here, our discussion will be limited to good transactions. You see what I'm saying? Good transactions, legal transactions, right? Because a transaction will have to be well written, right? If the transaction itself tries to do something bad, and then this is a different type of issues. You see what I'm saying? Okay. So if you think about it, so our life is already very complicated. Even if all the transactions are good transactions, you see what I'm saying? They do not try to do bad things, right? So we assume that all these transactions are good transactions, and our mission is to serve them well. You see what I'm saying? To serve them well. Okay. And of course, you can also say, well, what if somebody deliberately tries to submit a bad transaction, right? So this transaction tries to introduce some errors, purposely into the database. Well, to be honest, that's not something we can discuss in this lecture. Okay. In fact, such kind of behavior is prohibited, by some other means. So, for example, if you are caught doing something like this, and then you are fired, or there could be legal consequences, things like that. Okay. However, that's not within the topic of our discussion. Okay. So we assume that transactions are good transactions. Okay, they are legal transactions, right? So what do I mean by legal? So once again, this is a scientific course. I have to formally define what it means by legal, right? So a legal transaction says, okay, before the transaction, let's say the database state is consistent. And then, after I run your transaction, the database state will change, right? Okay, so the new database state will have to satisfy all the constraints. This is not a stringent requirement, right? Come on, your transaction will have to respect all the database constraints, right? So you cannot say I deliberately violate your primary key constraint. Actually, such kind of constraints will not be allowed by the database anyway. But I assume that you do not try to do something like that, okay? So a transaction is illegal, once again, if I execute it normally, I execute it completely, and then the database state will go from one consistent state to another consistent state. Okay, so if this is the case, and then I call your transaction a legal transaction. Okay. Well, as I said, right. So in the rest of this course, we'll be talking about legal transactions. Okay, we'll serve the purpose of serving legal transactions. Okay, we'll support legal transactions. Okay. All right. Now here, if you look at the red box, right? If you look at the red box, right? So this is something that is very, very important. All right. So if you look at a transaction from the execution point of view, a transaction is like a bundle. It's all or nothing. Okay. It's the only thing that is get at, before and after the transaction, the database state will have to be consistent. However, if you think about it, a transaction is like a it's like a sort of like a repairing process, right? So it's like something that will have to change the database state, right? So during the process of changing, of course, you cannot be so demanding, right? Because the database is changing. So for example, let's say I am modifying some value, right? So let's say there is some sort of constraint like a plus b. Oops, sorry. So this a plus b will have to be, let's say, some constant value 100, right? So this could be a user-defined constraint. You see what I'm saying? I could say, there are two particular tuples and particular values, and the sum of these values will have to be 100, right? So if you change the value of one, if you change the value of one tuple, and then you also have to change the value of the other tuple so that this equation can remain valid, right? So if you think about it, this is required by a consistent database state. However, during the transaction, right? So when I change the value of A, the value of B has not been changed, right? So it's impossible for me to satisfy this equation at all times during a transaction. You see what I'm saying? That's simply not possible, right? So this is another thing that would confuse a lot of students, right? So some students would say, hey, you know what, during the transaction, look at this particular moment, right? So the database state is not consistent at this particular moment, right? And the answer to that question, the way to clear that confusion is to say that this is all right. Okay, this is all right. In fact, that's one of the reasons why the notion of a transaction is so important. You see what I'm saying? Okay, the database knows, the system knows that in some cases, I mean, for a certain type of constraints, it's very difficult to enforce it at all times, strictly at all times, every single second, all right, simply because of issues like this, okay, issues like this, right? So for that reason, the database does not require, the database state to be consistent at all times, at every second. It's all right only, I mean, it's all right as long as the database state is consistent at the end of the transaction, right? After the transaction has either committed or aborted. Okay, so this is another very important design of the database system. Okay, all right, cool. All right, now let's bring in another very important concept. All right, so this is the concept of schedule. All right, schedule. You see, so far we have been talking about just individual transactions, right? So now here is the first time that we see two transactions. Okay, two transactions, T1 and T2, right? As I mentioned several times already, in the database system, you could have multiple transactions running at the same time, all right? And the database, after all, will still have to execute one instruction at a time, right? Even though there are multiple concurrent, transactions, the database will still have to give attention to every transaction in some, by taking turns. You see what I mean? Like, for example, your Windows system is one such kind of a multi-thread system, right? So you could be running multiple programs at the same time. So that gives you the illusion that as if, every program, all the programs are running at the same time. However, what really happens, behind the scene is that the CPU attends to every single program in turn. You see what I'm saying? Like it processes, program A a little bit, and then it suspends the execution, and then it turns its attention to program B, executes a little bit of that, and then it goes back to A and then executes the next few instructions, and then it goes back and forth, right? In this manner, A and B seem to be progressing concurrently. However, really behind the scene, there's only one CPU. Okay, so you can imagine similar things happen in the database system as well, right? I have two transactions here. However, there's only one CPU, so you know that at any moment there's only one instruction being executed, right? So this gives rise to the notion of schedule, right? Now, this schedule typically concerns multiple transactions, right? It is still a sequence. You see what I mean? A transaction itself is a sequence of instructions, right? And so is a schedule. Okay, and this is very normal. This is not surprising. This is very expected because, as I said, there's only one CPU, right? So the CPU can only execute a sequence of instructions. But the thing is, this sequence of instructions might come from multiple transactions, right? So here, in this example, I'm showing you a schedule, right? So the schedule basically says, this is in this sequence, right? So this is the first instruction executed. So it comes from T1, right? It reads some tuples value, right? So A, right? And then this is the second instruction executed. As you can see, it reads another value, all right? Not the same value, right? So A is one value and B is another value, right? So if you look at it, this is pretty clear, and every transaction tries to increment one particular value, right? But different values. You see what I'm saying? Okay. So these transactions they are running in parallel. However, according to the schedule, we say, look, there is still a sequential process here, right? So there's a sequence here. It's 1 to 8. All right. So next time when you hear me say schedule, all right, do not think that this is really, really involving parallelism. Okay, it does not. All right, a schedule is still something serial. You see what I'm saying? It's like a sequential execution. However, it might interleave the instructions of different transactions to give you the illusion as if all those transactions were running. Okay, so this is the notion of schedule. Okay, schedule. All right. So now this is a point that could confuse some students, right? Because a schedule is a sequence and a transaction is also a sequence, right? So what are the differences, right? So the difference is a schedule typically concerns the instructions coming from multiple transactions, right? But so when I define a transaction, it's an atom, and an atom, it's all or nothing, okay? So a schedule is sort of like interleaving the instructions from multiple atoms, all right? But a transaction itself is just a sequence of transactions that's meant to satisfy the all or nothing requirement, okay? All right, so that's the meaning of schedule. Okay, cool. All right, very nice. So we are progressing well. Now, I'm going to introduce another very important notion, okay? Serial schedule, okay? Serial schedule, all right? So you already know what a schedule is, right? So a schedule is a sequence of instructions from multiple transactions, right? Now, if you look at this schedule here, is this a schedule, first of all? Okay, oops, I'm sorry, what happened? Yeah, okay. So this, of course, is schedule. As you can see, this is, a sequence of instructions, right? A sequence of instructions. And actually, these instructions come from two transactions, right? So it satisfies the definition I gave, right? So this is a schedule, right? However, this schedule is a very special type of schedules. You see what I'm saying, right? Why? Because as you can see, right, the first four statements come from transaction T1, right? And then, completely, if you look at T1, right, all the statements are here, right? T1 commits at instruction number 4, right? And then after that, the instructions of T2 come in, right? So now you can see it's like T2 starts after T1 has completed, right? So you can see there's a fine boundary, there's a fine line, okay, fine line, okay? And the line is here, right, between these two transactions, okay? So in this case, we say that the schedule is a serial schedule, okay? So formally, as you can see, right, a schedule is serial if there's no interleaving. You see what I'm saying? There's no interleaving, right? So you understand the meaning of this word interleaving, right? So there's no mix up among the instructions of various transactions, right? So if this is the case, and then this is called serial, all right? Now, let me ask you a trap question. Now, pay attention, right? This is a trap question, right? So if I have T1 and T2, right? So two transactions, how many serial schedules there are? Okay, how many serial schedules there are? Okay, so don't say just one, right? So you are witnessing one serial schedule here. However, if you say one and then you fall right into the trap, all right? There are two serial schedules, right? So if I represent this serial schedule here as T1, T2. Now if I say T1, T2, this tells you precisely how I would like to execute it serially, right? So basically I say you execute all the instructions of T1 first, followed by T2, right? But I could also say T2, T1. You see what I'm saying? Okay, so I say you execute all the instructions of T2 first before you execute instructions of T1, right? So this is another serial schedule, right? So there were actually two, right? So in general, this notion of serial can be generalized in an obvious manner to an arbitrary number of transactions. You see what I'm saying? So here, this is just an example with two transactions, but there could be three transactions, there could be four transactions, right? So here is a follow-up question. So let's say if there are k transactions, okay, how many serial schedules schedule, right? How many serial schedules there are for k transactions? Well, the answer is k factorial. Okay, k factorial. So this is basically the number of permutations there exists on k transactions. All right. Okay. So if a schedule has no interleaving, and then it's a serial, right? So this is the definition I gave you, right? However, if this condition does not hold, and then the schedule is not a serial schedule, right? And if it's not a serial schedule, and then we say concurrent schedule, right? So basically, concurrent schedule means not serial. All right, I just don't want to say not serial, because that doesn't sound cool, right? Concurrent schedule, that sounds really cool. Okay. All right. Now, serial schedules are very important, all right, because a serial schedule is very easy to analyze. Okay, a serial schedule is very easy to analyze. Why? Well, because we have already defined a transaction to be a good transaction. You see what I'm saying? Okay, so if I execute T1 in full, right, completely. So what did I say about the database state, right? So the database state, you see, this is the state before the start of T1, right? So the database must be consistent at this moment, right? And because the transaction is illegal, right? And as we already defined, right? A legal transaction always transforms one consistent database state to another consistent database state, right? So this means that the transaction will leave the database in a consistent state here, right? And then T2 takes over, and then the same argument can be applied to T2. Basically, before T2 starts, the database is consistent, and therefore after T2 finishes, the database must still be consistent. You see what I'm saying, right? So this argument can be applied inductively, and therefore you can lead to this very important conclusion, right? Serial schedules, they are no-brainers. You see what I'm saying? No-brainer, right? No-brainer here basically says, for sure, serial schedules must be good, right? They must be very safe. Serial schedules, they are perfect in terms of consistency, right? Because they always leave the database state in a consistent state, right? Okay, cool. All right, so if that is the case, a very natural question comes up at this moment, right? If that's the case, right, why not just use a serial schedule, right? And let's be done with it, right? So do nothing but serial schedule, right? So that's very easy to analyze. Why not, right? Well, you already know why not, right? So if you execute the transactions in a serial manner, and this is just like your Windows system or your Mac system, they execute one program at a time. Okay, so you cannot you cannot be listening to me on Zoom, and on the other hand, you are looking at some interesting website, on Chrome. I think some of you might be doing this. You cannot do something like this, right? You see what I'm saying? And this creates very, very bad experience for the users of the database system, right? So you want to create this illusion that multiple systems, they were running at the same time, right? And therefore you cannot rely on serial schedules. You see what I'm saying? Okay. All right. So I've been talking for a long time. So this is the second checkpoint I like to create. So I want to get some response. Okay, so I'm seeing some response already. Okay, very good. Excellent. Okay, it seems that you are getting the idea. Okay, cool. Very nice. Okay, so we have talked a lot about the requirements. Okay, so here, the next requirement is super, super important. Okay, so you already understand what a schedule is. Okay, now here is something very important. Okay, so this is something that every single database system will have to do. Okay, now hear me out on this. All right, so I'm about to introduce something extremely, extremely important. All right, so this is one thing that all the database systems will have to enforce on the transactions. All right, so this is the notion of recoverability. Okay. So before I go into the definition here, so this definition, involves some symbols. Okay, so we'll come back to the definition because it may not be so easy to understand directly. Let's first look at this example, right? So this is a bad schedule. You see what I'm saying? If one database system does something like this, and then this database system will create trouble sooner or later, okay? And no one will pay for it anymore very, very soon, because this is definitely going to create some chaos, some very, very serious and severe chaos. All right, so let's see what happens here. Okay, now let's look at T1, right? So the schedule, right? It starts with T1, right? So see, this T1 wants to read the value of A, from some tuple, right? So let's say this is a bank account. Is what I mean, like bank account. Okay, so let's say originally the value of A is say 100. Okay, good. Now T1, gets this A, right, into the main memory. So now it's 100. Now here, T1 would like to increase it, right? So this is like 101 now, right? Okay, good. So T1 will, next will write it back to the disk, right? So let's say the IO is successful. Okay, so now if I ask you, what's the value of A on disk, and then you should say it's 101, right? Correct, 101. Okay, cool. All right, so now you see T1 has not committed, right? Because this is a concurrent schedule, right? So maybe the CPU decides that at this time it should give attention to T2, right? So another T2, another transaction starts, right? Okay, so now let's see what the transaction is doing. Basically, it's a copy of T1. You see what I'm saying? It's doing exactly the same thing. So for some reason, the transaction would also like to add $1 more to this bank account, right? So it starts by reading A. Okay, so if I ask you what is the value of A, and the value of A should be 101, right? Because T1 has already updated it. And okay, so T2 now adds 1 to the value of A in the main memory. So now it becomes 102. All right. Okay, good. So now T2 writes the value of A back to the disk, right? So if I ask you what is the value of A on disk at this moment, and then you should tell me that's 102. You see what I'm saying? Okay, it's 102. All right, and then T2 commits, and the commit is successful. All right, so T2 is all done. All right, all good. All right. All right, cool. Do you see the problem now? Okay, do you see the problem now? Okay, so now the execution goes back to T1, right? Okay, what if, let's say I'm the villain, all right? I'm the bad guy, right? So I unplug power here, okay? Now remember, as a database system, you will have to be prepared for the worst, all right? So that's one big challenge for database systems. Okay, seriously, this is one big challenge for database systems. Okay, you have to be prepared for the worst case scenario, even though it might happen with a very, very small chance. However, you cannot take chances. You see what I'm saying? Because our lives depend on database systems. For example, our bank accounts, right? I can tell you all the banks. I mean, every single bank, every single person's bank account is managed by some database systems. All right, so those are systems that really, really enforce very, very high level of security and safety. All right, so for example, let's say right here, right at this moment, when the schedule executes to this red line here, right? So let's say some villain, some bad guy, me, okay, I unplug the power. And then what would be the issue here? Okay, what will be the issue? The issue is, you see, T1 has not, T1 has not committed. You see what I'm saying? T1 did not manage to commit, right? And therefore, T1 will have to be abort. Abort. You see what I'm saying? Okay, so T1 has made some changes to the database, and therefore, T1 will have to get rolled back, right? You see what I'm saying? Roll back. Okay, roll backed. Okay, will have to be roll backed. Okay, actually, you know what? The correct English should be this. Okay, roll back. Okay, so it needs to be rolled back. Okay, but if you think about it, T2 has committed. You see what I'm saying? T2 has committed, right? And therefore, the changes made by T2 will have to be made permanent. Do you see a contradiction now, right? Look, on the one hand, this 102 here, this is a change. This is a modification made by the second transaction T2, right? So this 102 will have to exist on disk permanently. So this is one thing the database system will have to do, right? But on the other hand, if you think about this 102, right, it involves the update created by T1. You see what I'm saying? And therefore, this value has been contaminated. You see what I'm saying? It has been contaminated, all right? It's dirty, okay? It's dirty. And therefore, the database system is facing a contradiction. It has no ideas how to proceed, all right? Now, guys, you are a person, you are a human being. You will be able to say, hey, you know what? At this case, maybe we should just change this 102 back to 101, okay? Yeah, sure, you can do this because in this very special scenario, in this very particular scenario, this is something you can do. And you can use logic to convince yourself that this is the right thing to do, right? However, in practice, the database will not have the ability to do this type of analysis every single time. In fact, these are just very simple transactions, right? If you have something very, very complicated, it will be very dangerous to rely on such kind of analysis, right? So what if you make a mistake, right? You make a mistake and then you might create some errors in the database system forever, right? You don't know. It's just a matter of time that such kind of errors will create serious inconsistency issues. Okay. All right. So you can see this is a problem. All right. So the database system decides, actually all database systems in the market decide to prohibit such kind of behavior by saying that every single schedule executed in a database system will have to be so-called recoverable. Okay, recoverable. So what's the meaning of recoverable? Okay, now let's see why this schedule is not recoverable. All right, you can see that this value of A, so let me point it out for you. All right, so this value of A, all right, so this read, all right, this read is dirty, dirty. Now, what's the meaning of dirty? So dirty says, you see, this value of A is changed by this transaction. All right, so this is this is modified by this transaction. This is written by transaction T1. However, T1 has not committed. Okay, T1 has not committed. So let's write this down. You see this A modifying by T1, and T1 has not committed. Okay, has not finished. Okay, and therefore you have no idea whether the value is permanent or not. Actually, it may not be permanent, right? So if I unplug the power before T1 commits, and then this value will have to be rolled back, right? And therefore, you're not supposed to rely on this value, okay? All right, and this is a dirty read. Okay, so once again, a dirty read says that a transaction such as T2 reads a value that has been modified by another transaction, and that transaction has not committed yet, right? So that transaction is still running, okay? And you cannot read that value, all right? So every time you read a value, you have to be sure that this value is permanent, okay? All right, good. Now it's time to look at this recoverability definition, right? So it says, well, if you have a transaction T, such as T2 here, okay? So this transaction reads a value written by another transaction, T prime, okay? So this T prime is T1 here, okay? And then, this T2 will have to commit after prime, right? So you see here, T2 reads a value of T1 modified by T1, and therefore T2 should commit after T1, not before T1. You see what I'm saying? Okay, you see here T2 commits before T1 commits, and that's not allowed. All right, so that is not allowed, right? So you have to swap. Okay, you have to swap. Oops, you have to swap these two commitments. Okay, you have to swap these two, not commitments. Okay, I used the wrong noun. I should have said these two commits. Okay, you should swap these two commits, right? So you should let T1 commit first, and then T2 commits later. You see what I'm saying? So this gives T2 a chance to undo itself, right? So let's say if T1 is rolled back, right? And then T2 says, oh, T1 is rolled back, and I have read something dirty, and this thing is modified by T1, and therefore I cannot commit, right? Because this value is already dirty, and I have to roll back myself as well. Okay, if that is the case, and then it will be recoverable, right? However, this schedule here is not recoverable because T2 currently commits before T1, all right? And this is not okay, all right? And according to the recoverability schedule, according to the recoverability definition, this is not okay, all right? So T2 will have to commit after T1 if it reads a value modified by T1, okay? All right, now this is a very, very crucial notion, okay? I want to have a quick check. Is this clear to you? Okay, if it's clear to you, type something, okay? Regarding recoverability, what happens if T1's commit goes through? Will the value of A on disk be reverted back to 101? So I don't understand the question completely, but I can take a guess. Okay, I think the question says, what if I simply use this schedule? Okay, what if I simply use this schedule, right? If T1's commit goes through, if T1's commit go through, it means everything goes through. Okay, I see. So I think the question says, what if I have to run such kind of schedule anyway? Right? So what will be the value of A afterwards, right? So this is a trick question for me, Nichols. Okay, so I can tell you this question does not exist. Okay, I'm not going to answer this question because no database systems will allow such kind of schedules. All right, so your question will simply not exist in practice. Okay, it does not apply in practice. Okay, Nico. All right, so that's my answer for you. Okay, so it will not exist. You see what I'm saying? No database systems will allow such kind of schedules. All right, so every single database system will execute only recoverable schedules. All right, so your question is an interesting question, but it does not have an answer. Okay, all right, cool. All right, so nice. Okay, very nice. Okay, now so let's move forward. Okay, so let's move forward. All right, so we will be talking for another 10 minutes and then we'll take a break. Okay, all right. So you have learned a lot about transactions and schedules. Okay, all right, now let's see another notion. Okay, so so this notion talks about equivalence. Okay, equivalence, right? So formally speaking, if you have two schedules, right? Two schedules. So two schedules, they are equivalent if they always transform one database state to another database state. Okay, so before and after those two states, if these two schedules they are run on the same database state, and then they always end up with the same database state. Okay, so if this happens, and then the two schedules are said to be equivalent. Okay, now in order to demonstrate, look, here in this example, we have a concurrent schedule, right? So you can see, this transaction, right? So this transaction T2, okay, it basically increases the value of A on the disk, right? Okay, and then T1 comes along, T1 reads the value that's changed by T2, right? And then it will set another tuple's value to this particular value, right? So this is what T1 does, right? And then T2 commits, okay, T2 commits, and then T1 commits, right? So therefore, this schedule is a recoverable schedule, right? Because you can see this read is dirty, right? However, that's fine because T2 commits first, okay? So this is recoverable, right? Because if T2 something wrong happens to T2 and T2 needs to be rolled back, and then T1 can also, roll back itself, right? Okay, now the thing is equivalence here, right? The point is equivalence, right? So now think about another schedule, right? So compare the schedule to the serial schedule of T2, T1. You see what I'm saying? So when I say T2, T1, I mean I execute the entire T2 first, right? So this means, these four instructions are executed before these four, all right? You know what? Let me be very, very precise. Okay, let me give you some sequence numbers. Okay, so think about another schedule, right? So the schedule says 1, 2, 3, 8. You see what I mean? So that's basically T2, right? And then another followed by 4, 5, 6. Oops, no, this is not 8. I'm so sorry. This is supposed to be 7, right? And then 4, 5, 6, 8, right? So this is T1. Okay, you see what I mean? All right. So now I have two schedules for you, right? So this schedule and also this schedule, right? So convince yourself, right? If these two schedules, they are executed on the same database state, right? So before the two schedules, if they, the database stays the same, and then, they will create the same effect afterwards, right? Well, as you can see, basically this commit statement can be moved, before this read, right? So without changing anything, right? So if this is the case, and then we say, these two schedules, they are equivalent, all right? So they are equivalent, all right? So as you can see, this equivalence, right, really benefits from our formalization, right? So you see, we have come a long way in this scientific discussion, right? So you see, when we talk about science, we have to be completely clear on the definitions, right? You can see, this definition, this is not a trivial definition because it involves a lot of new concepts, right? For example, database state, right? And then schedules, right? And then here it's defining equivalence. However, amazingly, if you look at this definition, it's perfectly clear because everybody in the world will have to interpret this this definition in the same way, right? So this is the power of formalization. You see what I'm saying? This is making things absolutely clear, right? So now you understand what's the meaning of equivalence between two schedules, right? So it's very, very important to remember that, you know, if you claim two schedules to be equivalent, and then the following will have to hold, right? So if I execute the two schedules on the same database state, I always get back the same database state, right? So for this reason, if I say, okay, how about T1, T2? Okay, you see what I mean? T1, T2, right? T1, T2. All right, so if I say, is this schedule equivalent to T1, T2? Okay, you know what? I will be very precise for you. Okay, T1, T2, right? So let's say I do 4, 5, 6, 8. Okay, and then followed by 1, 2, 3, 7. Can I say that, you know, this concurrent schedule is equivalent to T1, T2? Okay, the answer is no. Okay, the answer is no. All right. Why? Because, you know, you can easily convince yourself, right? Let's say initially A is 10, and let's say B, I don't know, it doesn't really matter. Let's say A is 10 and B is 7, right? So if I execute this concurrent schedule, right, at the end of the schedule, right, what will be the database state? You know, this A will be 11 and B will be 11. Right? So this is the outcome of the concurrent schedule. However, if I run T1, T2, right, what would be the database state afterwards? Okay, what will be the state afterwards? The state will be, you know, A is what? A is, let me see, I execute T1 first, right? So A will still be 11, however, B will be 10. You see what I mean? Okay, because if you you know, execute T1, right? So this is going to set the value of B to the original value of A, which is 10, right? And then after that, you will run T2, and then T2 will increase the value of A by 1, right? And therefore, this schedule is not equivalent to this schedule because they might create different database states. All right. Okay, so this is the notion of equivalence. You see what I mean? This is the notion of equivalence. Okay. All right. All right. So let me check with you once again. Do you understand the notion of equivalence? Because this is super important. Okay, this is super important. Okay, do you understand? You know, there are 3 schedules here, right? These 2 are equivalent, but these 2, they are not equivalent. Okay. All right, cool. All right, very, very nice. If this is clear to you, well, here now there's one big elephant coming into the picture. Okay, now this is serializable. Okay, so this is one super important notion. All right, so this is extremely related to your project. Okay, so your project, if you look at the second part, right, about transactions, so there you have to fully understand to do that part of the project, you have to fully understand serializability. Okay, now let's look at the same schedule, right? So this is the same schedule that I talked about on the previous slide. So here you can see this is a concurrent schedule, right? So we already know that this schedule is equivalent to T2, T1. So this is the conclusion from the previous slide, right? Now, if this is the case, and then we say that the schedule is serializable. In other words, this schedule is serializable, okay, as stated here, all right? The schedule is serializable, all right? So this essentially says what? You know what? Even though the schedule is concurrent, it looks concurrent. However, this concurrent schedule is definitely fine. Okay, it's definitely fine. You know what I mean? You still remember that every serializable schedule is definitely fine, right? In terms of consistency, all right? It will never leave the database in an inconsistent state. Why? What is the proof? What is the argument? You see, a transaction is defined in such a way that if you run a transaction serially, one after another, right, it will always change the database state from the original state to one consistent state, and then to another consistent state, and then to another consistent state. You see what I'm saying? So serializable schedules, they sort of like they serve the purpose of a life circle. You see what I mean? We can hold on to the life circle in order to analyze whether the database state is consistent or not, right? And therefore, if we say, look, this concurrent schedule, and we want to prove to people that this concurrent schedule is safe, right? It will always be leaving the database state in a consistent state, right? What is the argument? Now you can prove that, well, because this concurrent schedule is equivalent to this serial schedule, and all serial schedules are good, and therefore this concurrent schedule must be good, all right, must be safe, must be leaving the database state in a consistent state. You see what I'm saying? So this is the argument. All right. So guys, very importantly, this is serializability does not say that the schedule will have to be equivalent to all serial schedules. All right. So this is not all. You see what I'm saying? This is not all. If you say all, then it's wrong. All right. It's incorrect. All right. Actually, it's impossible. You see what I'm saying? Let me look at T1, T2, right? In general, T1, T2 is not equivalent to T2, T1. You see what I'm saying? All right. However, this is serializability. If you think about the purpose, right? As I explained, the purpose is to argue that this particular current schedule is fine. You do not need the schedule to be equivalent to all serial schedule. You only need the schedule to be one serial schedule, and it suffices. Only one is suffices. You see what I'm saying? And this is just like you have two transactions, right? You have two serial schedules. No matter which serial schedule you use, right? You run T1 first or you run T2 first, it doesn't really matter, right? The ultimate state may not be the same. Did I lose the connection? Okay, all right. So now you can see. Sorry. Now you can see the previous slide, right? So you can see, if I run T1 first, or I run T2 first, I might create different database state. You see what I mean? If I run T1 first, and then I get this state, right? If I run T2 first, and then I get this state, right? However, both states are acceptable. Why? Because we already know, right? Transaction T1 is legal. You see, that's the power of formalization, right? So transaction T1 is legal, right? Which means if I run T1 first, this database state must be consistent. So this is fine, all right? So if I run T2 first, right? And this state must also be fine. You see what I mean? Okay, there could be multiple legal, consistent database states created depending on which transaction you run first, right? So that makes sense in practice, right? I mean, both transactions are legal, and depending on which one runs first, the concrete values of the tuples might be different. This is okay. This is accepted, right? And by formalization, we capture this, right? Because we say T1 and T2, both of them will have to be legal, all right? All right, coming back here, this is the rationale behind serializability, all right? As long as it's equivalent to one serial schedule, and then it will be all good, okay? So we say that, such kind of schedule is serializable, okay? And if this schedule is not equivalent to any serial schedule, and then we say this is non-serializable, okay? So here, before we take a break, let's take a look at one example of a non-serializable schedule. Okay, you see this is non-serializable. Okay, well, let's take a look at it, right? Let's take a look at it. Look, so here, if you look at each transaction, right? So the purpose of each transaction is to increase the value of A by 1. You see what I mean? Okay, so if you look at a serial schedule, right? So there are two serial schedules here. This is T1, T2, and then you have another possibility, T2, T1, right? So if you look at the effect of each serial schedule, right? So if I ask you, right, if you run T1, T2 or T2, T1, how much should A be increased at the end, right? Compared to the beginning? Well, the answer is, A should be increased, should go up by 2. You see what I mean? All right, because each transaction will put $1 into the account, right? So you know that the database state should be in such a way that A should go up by 2. All right. Now, if you look at the concurrent schedule, okay, and look at the effect, right? So here you can see, let's say A initially that is 10 on disk, right? On disk, okay. So now here T1 reads A into the memory copy of A. So this is the memory copy of T1, okay? So the memory copy of T1 now it is 10. You see what I mean? Okay, good. So now T1 changes the value of A in the main memory, all right? So this is doing in the memory copy of T1. You see what I'm saying? Okay, so the memory copy of T1 now becomes 11, right? Oh, by the way, what is a memory copy? I mean, this is just like a variable that you define in your program, right? So you can imagine a transaction to be a program, a Python program, right? So this Python program connects to the database, and here this will be one SQL statement, let's say, right? A one SQL statement. So you get some value, and then you copy this value into your, so you get this value into your one of your local variables, right? So this A here, this memory copy here refers to some local variable for your program. You see what I mean? Okay, so in that program, you change the value from 10 to 11. Okay, so okay, now the execution goes to T1, sorry, T2, right? So likewise, T2, this has another memory copy. Actually, T1 and T2 might even be from different computers, right? Both of us could be connecting to the database simultaneously. You have your program and I have mine. You see what I mean? Okay. So now let's look at this part, right? So this part will read the value on the disk. You see what I mean? T1 and T2, they do not see each other. They are even on different computers, right? So the memory copy of A for T2 is still 10. Now, this is something very important. You understand what I'm saying? Okay. All right. Now, you execute the next statement. So this statement changes the value of 10 to 11 for T2, right? So this is a memory copy of T2. Okay, cool. Now, the execution goes back to T1. All right. So now we are executing this write A, right? So now if you execute this, right, the value, now this is like an update statement, update SQL statement, all right, done by your Python program, right? So now this is going to change the value of A to 11 on disk. You see what I'm saying? Okay, good. Now the execution switches to T2, and T2 now also writes its own memory copy to the disk, right? So now it's writing 11. And then you can see it's not going to change the value of A on this because it's already 11 there, right? Okay, so both transactions think that they have increased the value of A by 1. Okay, so each one of them commits happily, but you know better, right? So the value of A has increased by only 1, not by 2. You see what I'm saying? And therefore, this is a proof showing that this schedule is not serializable. Okay, because I explained earlier, right? If you execute things serially, the value of A should have increased by 2. And therefore, this is not serializable. Okay. Well, as you can see, this slide tells you something very important, right? So if you execute multiple transactions concurrently, something could go wrong, right? So this serves as wonderful evidence, right? Showing, for your eyes, directly, right? What could go wrong, right? So you see, you run transaction T1, I run transaction T2. We are not aware of each other, right? Each one of us thinks that we must have done something right. right? Okay, but in the end, this account, this poor guy, I don't know who owns this account, right? So this guy thinks that he or she should be getting $2, but this person ends up getting only one, right? Well, the reason is the database does not use a serializable schedule. Okay, guys, do you understand this? All right, if you understand this, give me something, please. Okay, give me something, please. Okay. So give me some feedback. Okay. All right. Excellent, excellent. All right. So if that's clear, I think we deserve a break, right? So let's break for 5 minutes and then we'll move on. Okay. So we will resume at, let me see, 55. Okay, 1:55. See you later. Okay. See you. Okay. Sorry. I muted myself. I'm sorry about that. Okay, so let me redo this part. Okay. All right. Let's continue. All right. So this is really resuming the second part. Okay. So second part is about isolation levels. I muted myself just now. I realized that. Okay. So let's continue, right? So as I was saying, you already know our purpose is to discuss concurrent schedules. Okay, concurrent schedules, right? And concurrent schedules can create strange phenomena. Okay, they can create issues that can never exist in serial schedules. All right, we already saw some. We already saw. We have already got one idea, some idea about such kind of strange phenomena, right? We've seen one. Okay, we saw one just now, right? And um, in the second part of the lecture, I'm going to show you more. Okay, but before I go on, let me tell you, in the database jargon, right? So usually we refer to such kind of strange phenomena as anomalies. Anomaly. Okay, so this is a really a very nice word saying something unusual. Okay, unusual. All right. Well, you will know that some of these things are, I mean, all these things are weird, right? So that's why they are anomalies, right? However, it's very interesting to note that the database system may choose to allow some of these anomalies, okay? And you will understand why later. Okay, you will understand why later. Okay, but the thing is, the database system will have to be very clear about which anomalies can exist, in the system. All right, so this is really like a pre-announcement about the side effects of some drug that you are taking to treat some issues. You see what I'm saying? All right, you have to make an announcement in advance so that users know what to expect. You see what I'm saying? Okay, so such kind of announcement is called a policy. All right, so this policy is what we call isolation level. All right, so in the second part of today's lecture, I'm going to talk about this isolation level. All right, so I will go step by step. I will first explain what anomalies you could have in a database system, and then I'm going to talk about different policies. All right, so different announcements, standard announcements. Okay, what kind of anomalies will be allowed in the system? Okay. All right, let me just double check. I think you can hear me, right? Let me see. Yes, I think so. All right. Okay, now let's look at 4 anomalies. Okay, so I'm going to illustrate 4 anomalies. All right, so these are not meant to be all the anomalies that you could possibly find in a database system. All right, however, these 4 anomalies are especially common, okay, and especially important. They are so important that they directly affect this isolation level policy, uh, which we'll be defining at the end of this presentation. Okay. Now, this is something we have already seen. Okay, so I'm not going to talk much about this because this is exactly the last example that I demonstrated, right, in the previous presentation, in the previous with the previous set of slides, right? So you can see here we've got a concurrent schedule, and this concurrent schedule is not serializable, right? And as I defined at the beginning of this presentation, I said, what is an anomaly? Still recall, right? An anomaly refers to a phenomenon that cannot exist, it cannot happen on serial schedules, right? So this is a phenomenon. This is called the non-serializability phenomenon, right? Non-serializability. How did I prove that this schedule is non-serializable? The proof, the argument says, look, if you execute this schedule, the value of A is only increased by 1, all right? But that's not possible, right? Under any serial schedule, right? Under any serial schedule, the value of A will have to increase by 2. And therefore, this is an official proof that this is not serializable, okay? All right, now let's look at the second strange behaviors, strange phenomenon, okay? The second anomaly, this is called phantom, all right? So let's directly look at this example before we go to the formal definition here, all right? So here, let's say that I have a relation here with attributes X and Y, okay? And there are 2 transactions here, okay? T1 and T2. Now remember, these 2 transactions, they are not aware of each other, right? So my favorite example is saying, I could be running transaction T1 on my computer. You see what I'm saying? And you could be running transaction T2 on your computer, okay? And both of us connect to the database. A database is just a port, sorry, the database system is just some software running on some server, right? And this server will be listening to connection requests at some port, right? So if you do the project, if you have already played with PostgreSQL a little bit, and you know that the port number for Postgres is 5432. Okay, so that's very interesting port. Okay, 5432, right? So that's what happens, right? So imagine that this Postgres system is running on some server, and I am connecting to the server with T1, and you are connecting to the server with T2, right? So the point is that we are not aware of each other, okay? So on my side, I run this query, okay? I run this query. I say, okay, I want all the tuples whose X values are equal to 1, okay? And then, I plan to do something with this query, and then I'll run it for a second time. You see what I mean? So what do I expect with these 2 queries? Well, they are the same query, right? Because on my side, I will be saying, since they are the 2 queries, and since I didn't do anything to the database, and therefore, I should expect that both queries, they return exactly the same result, right? That's a fair assumption, right? At least I know this will have to be true if my transaction was the only transaction running in the system, right? And just like in a serial schedule, if my transaction is the only transaction running in the system, definitely I should be expecting this, right? So once again, what I should be expecting is that the results of the two queries ought to be completely identical, okay? But the thing is, in between these two queries, you might be inserting a tuple into the relation. You see what I mean? Look, this relation, this tuple you're inserting has value 1, okay, on attribute X, okay? So now let's say the database somehow decides to use this schedule, okay, to execute this schedule, right? And then on my side, something very strange is going to happen, right? You can see the first query does not retrieve this tuple, right? Because the tuple did not exist by then, right? And then you make the insertion, and then I run the query for a second time. Oops, well, I can see this tuple now, right? So this is very strange. You see what I'm saying? Okay, now this is called phantom, like a ghost, right? This tuple comes out of nowhere, right? It's really like a ghost that comes into the picture. You see what I'm saying? All right. Now, formally, a phantom refers to a situation where executing the same query twice, okay? Executing the same query twice, just like what I'm doing here, right? And these two queries, they return different results, okay? Even though, the transaction performs no modifications on the relevant data. You see what I'm saying? So I did not perform any modification that would affect the output of these two queries, right? I run them twice, I get different results. And for me, that's like a ghost has come into the picture, right? So that's called a phantom. That's what I mean, phantom. Okay. All right, cool. So this is the second anomaly that could exist, okay, when you have concurrent transactions, okay, good. Now, let's look at anomaly number 3, okay? So this is a non-repeatable read, okay? So this time I don't have any queries, okay? I don't perform any queries, okay? However, I perform reads, all right? So now let's look at this particular scenario here, okay? So you see, by the way, let's ignore the definition for the time being, okay? So let's get some ideas from the example, and then I'll go back to the definition, all right? So now let's look at T2, right? So T2 performs the first read here, okay? So the value of A. So let's say A before on the disk, so A was 100 in the beginning, right? So now for T2, now A becomes 100 and A is 100, right? It just performed the read. Okay. So on T1, so let's see, right? Okay, on T1, so now A is 100, all right, and then the execution goes down to this statement here. It changes the value of A from 100 to 101. And now let's execute the next statement. So this statement updates the value of A from 100 to 101. You see what I'm saying? Okay, cool. Now the execution goes back to T2. Okay, so look at the read operation, the read operation in the blue ellipse. Okay, so as you can see, right? So this value of A, so this operation fetches the value of A from the disk. Okay, you have to understand every read operation gets the value directly from the disk, right? So it goes to the disk, and now you see, well, this read A returns 101. All right. Now, from the perspective of T2, this is very weird. You see what I'm saying? Because, absolutely, T2 has done nothing in between that could possibly change the value of A on the disk, right? And yet, as you can see, two consecutive reads, okay, two identical reads, right? They fetch different values of this A, okay? So this is a little bit like phantom, all right? Except that, you don't really have a ghost coming in, right? So if you look at phantom, you have a ghost. This is the ghost. You see what I'm saying? This is the ghost, right? But the idea is the same. The idea is very similar, right? So you perform, so you read the database twice, however, you get different results, right? And even though you don't really have any new tuple, right? So you can see this A is not a new tuple. You see what I mean? It's there. It's not a ghost. It's not coming in. It exists there. From the perspective of T2, we know about the existence of A. All right. So that's why it's not a phantom. Phantom is like we did not know that there was this A, but here we do know that this A exists, right? It's a non-repeatable read though, because we try to read this variable twice, but we get back different results, even though in between we did not do anything that could possibly change its value on the disk, right? Okay, so this is called a non-repeatable read. Okay, non-repeatable read. So let's look at the formal definition, right? So a non-repeatable read, is a situation where two identical reads, right? So just like this one and this one, right? These two are identical reads, right? They retrieve different information. You see what I mean? They return different things, even though the transaction, did not perform anything that could possibly change the value of the this variable, okay? And therefore, now we have and therefore this is a non-repeatable read, okay? So just like what we have in this example, okay? All right, okay. So this is anomaly number 3, okay? All right, now let's look at anomaly number 4, okay? So this is something we already talked about, actually, in the first part, when I talked about recoverability, okay, recoverability, I talked about what is a dirty read, okay? So here, this is the formal definition of this dirty read, okay? So look at the example first, okay? And then we'll look at the definition, all right? So this is something we saw before, okay? This is something we saw before, right? So you can see T1, all right? T1, it changes the value of A, right? It changes the value of A. However, T1 has not committed yet, right? Up to this point, T1 still running, right? T1 still running. Now, let's say T2, right? T2 comes in and it reads the value that has been changed by T1. You see what I'm saying? Okay. So this read is dirty. Okay. So let's write this down here. Okay. So this read, this is dirty. Okay. Why? Because according to the definition, now it's time to look at the definition, right? This read operation is dirty because it reads a value that was written by another transaction that has not committed yet, right? So this T1 has not committed yet at this point. You see what I'm saying? However, this read A gets a value that is changed by T1, and therefore this is a dirty read, right? So remember, we're talking about anomalies that cannot exist for serial schedules. You see what I mean? Okay, so this is definitely a situation that cannot occur on serial schedules, right? A serial schedule, there's only one running transaction, right? So all the reads must be from the disk, and the disk has already been committed, in the sense that all the transactions that modified the disk before must have already committed, right? So that's the definition of serial, right? So you can see this is indeed something that cannot exist on serial schedules. Okay, so I have explained 4 anomalies. Okay, 4 anomalies. So let's quickly go over all of them, okay, because this is important, right? The first one says non-serializability, okay, non-serializability, all right? So you can have schedules that are not serializable, all right? So this is a very typical scenario, right? So still remember the argument, right? So what is the value of A? I mean, how much has A been increased at the end of this schedule, right? Only 1, right? But that cannot happen, right? So this is the second anomaly, right? Phantom, right? So you run the same query twice, but then you see a ghost. right? And at the time of the first query, this ghost did not exist, right? But now it does, right? So that's why it's a phantom. Okay, and here we're talking about non-repeatable read. No phantom this time, no ghost, right? Because this A exists in the database. We know A exists. Okay, so we actually read it, right? But the thing is, we read it again, its value has changed, right? Out of nowhere, right? I mean, out of no reason, right? So the value has changed. So this is a non-repeatable read, okay? And finally, dirty read, okay? So before I move on, it's very important I solicit some feedback. Are these 4 anomalies clear to you, guys? Okay, so I'm going to define isolation levels, but before that, I want to make sure you understand anomalies. Okay, are these 4 anomalies clear to you? Okay, if they are clear, give me something, please. I want to see some feedback. Okay, good. All right, good. All right, you seem to be pretty confident about anomalies. All right, now it's time to talk about anomalies. Okay, talk about which anomalies, which anomalies, we should allow. Okay, so first of all, one thing very clear, one principle very clear. Okay, anomalies are bad things. Do not try to push too hard by saying, you know what, anomalies are good. That's nonsense. Okay, anomalies, of course, are bad, right? So that's why they are anomalies, right? We don't want them to happen. You see what I mean? We don't want them to happen. Okay. But there is another side of the coin, guys. There's another side of the coin. The thing is, if you say, okay, we try to prevent all of them, since they are bad, and then we kill all of them. We don't allow any of them to happen, right? Well, you could do that, but then the thing is, if you decide to do that, and then you could be severely reducing the concurrency level. You see what I'm saying? Okay. For example, you could easily kill all the anomalies by forcing all the execution to be serial. Okay, you could do that, but then your database system will be, intolerable. You see what I'm saying? This is just like, using an operating system that does not permit 2 softwares running at the same time, right? So this is unthinkable. You see what I'm saying? All right. So for a database system, this concurrency level is very important, right? Because you want to simultaneously serve multiple requests. You see what I'm saying? I'm connecting to the database. You are also connecting to the database. You really, really want us to feel that, as if, the database system is very responsive. You see what I'm saying? Very responsive, right? So you don't want any user to feel, wow, the system gets stuck, right? So this is not okay. You see what I'm saying? So, and also this is even necessary when it comes to fairness. You see what I'm saying? A fairness, right? So let's say both transactions are connected almost the same time. You want to basically give the same share of time to every single transaction, right? So this is even fair in that sense. You see what I'm saying? Think about situations where we could have stock market transactions, right? Stock market transactions, right? I try to buy a stock and you try to buy a stock. Let's say maybe my connection arrived a little bit earlier and then I will be blocking your transaction. You know what? I will be very happy if that happens, right? But this is not what happens in reality, right? People would not be able to tolerate this type of things, right? Okay. So that creates some sort of dilemma, right? Because you have 2 sides of the coin. So one side, these anomalies, they are bad. They are really bad things, okay? On the other hand, if you want to overkill them, all right? So, and then you will be reducing the concurrency level significantly, okay? So here, this is a place where this isolation level comes into the picture. So as I said, right, the database system deals with this issue by making a pre-announcement. You see what I'm saying? So basically the idea is, I will tell you in advance, okay, what isolation level will be guaranteed for your transaction. You see what I mean? All right, so if you want your transaction to be serializable, you can go for a higher isolation level. And then if that is the case, then you expect some more severe side effect. You see what I mean? This is just like, if you have cold, right? And then you go for a very, very heavy drug, right? And then, it will kill the cold, but it will also kill some of your healthy issues. You see what I'm saying? But you cannot blame people, right? Because you have selected the drug, right? So you have been informed of the side effect, right? Same thing here. So if you do the project, for example, that's why I said, it's very important for you to do the project, because that's going to give you real experience with the database system, right? So in the second part of the project, I designed those tasks in the second part in such a way that, you will be able to understand the differences of different isolation levels. All right, you'll be able to know when you start a transaction. Okay, for example, when you connect to the database, you can actually specify what isolation level you will be needing for this particular transaction. Okay. So next, I'm going to introduce the common isolation levels, right? So here, I'll be using the ANSI standard, right? So this ANSI represents American National Standards Institute, okay? So I'll be using the ANSI levels, right? So there will be four levels here, okay? The first one is the weakest, and the last one is the strongest, okay? So the last one, um, um, will have the poorest concurrency among the transactions. Okay, so this is sort of like a very strong, very heavy, very strong drug. All right, and the first one is a very light-weighted drug. However, this is going to create a lot of weird phenomena. Okay, so here let's look at the table. Okay, so I talked about four types of anomalies, right? But phantoms will be isolated. Okay, so phantom will be taken out. It's not something that's directly considered by the ANSI level. All right. However, there will be a patch. We will see there will be a patch here. Okay, so we will look at this patch later. Okay. Now let's look at the other three anomalies that I talked about, right? So I talked about non-serializability. I talked about unrepeatable reads. I talked about dirty reads, right? So trying to recall whether you still remember what they are, right? So that's why I solicited the feedback. I wanted to make sure you understood, what they are before we come here. All right. So let's look at serializability. Okay, sorry, serializable. So this is the strongest isolation level. All right. So this is the strongest drug. If you say you declare your transaction to be serializable, and then basically you are saying, nothing's weird can happen. Okay, no weird, no strange phenomena can happen to your transaction, right? So you'll be saying no dirty read, no unrepeatable read, and everything will have to be serializable. Okay. So let me tell you, such kind of isolation level is almost compulsory for critical transactions. You see what I mean? For critical. So for example, for the stock market, even though I use stock market as an example, in fact, stock market transactions, they will have to be serializable, like it or not, all right? And if we happen to be changing the same thing, and then yes, we will have to be serializable, okay? Even if it means blocking. Why? Because, this involves money. You see what I'm saying? Nothing can go wrong with money, okay? So these are critical transactions. You see what I'm saying? So for example, if two transactions are trying to add $1 to the same bank account, right? And these are critical transactions. What happened before like two transactions, both of them think that $1 has been deposited into the account, but in reality, this account is incremented, is credited with just $1. This kind of situation simply cannot occur. You see what I mean? Okay. So for serializable, for critical transactions, you have to enforce the serializable level. So this is the highest isolation level. Now you understand why this is called isolation, right? So this is basically saying how isolated those concurrent transactions will actually be. You see what I mean? So when you say serializable, then this is saying they are completely isolated, right? You can guarantee that the end effect is going to be like, different transactions, they are as if they were run according to some serial schedule. Okay. All right, now let's move up the ladder, right? So this is the ladder, right? So this is the strongest. Now let's move up, right? So as we move up, and then we allow some anomalies, right? So this is repeatable read. If you say repeatable reads isolation level, and then basically, things will have to be repeatable. So therefore, this is no, right? You cannot have any unrepeatable reads. And also, this dirty read is really, really like a very serious issue, and you should definitely say no to it. However, you will be allowed non-serializability. Okay, non-serializability. All right. So I will not talk too much about repeatable reads because this is not a very, very popular isolation level. Okay, and we'll talk about this recommitted much, much more. All right, but just so you know, in the ANSI standard, there is one isolation level which says repeatable read, and this is what it means. Now, for this course and also for practice, right, especially, for example, for Postgres SQL, for Oracle. Oracle, by the way, is a very famous database system. Okay, so for those systems, this recommitted is something very important. Okay, recommitted, right? So recommitted says still no dirty read. As I told you, right, I received this excellent question from Nico in the first part, right? So, oh, what if that goes through, right? So the answer is the question is inapplicable because no database systems will allow dirty reads. You see what I'm saying? Okay, so every schedule will have to be recoverable. All right. So as you can see, this recommitted isolation level says no dirty reads, but everything else is fine. Okay, everything else is fine. You could have unrepeatable reads. You could have non-serializability. That is fine. Okay. So I can tell you this recommitted level is very important in practice. Transactions are non-critical transactions. So let me give you an example about non-critical transactions, right? Think about library. You see what I mean? You go to NTU library website right now, and you try to search for some books, okay? And I can tell you, basically, you are connecting to the database, managing all the books. You see what I mean? And it's possible for you to see phantoms. Okay, what do I mean by phantom? So I do the search, I see, oh, Da Vinci Code, right? So that's a book by Dan Brown, right? So I can say, oh, there are still some available copies there. I'm very happy. Okay, so, all right. But the thing is, when I enter all the information, I try to secure the book. Oops, the database informs me, oh, the book is no longer available. But the thing is, the whole thing is one session, right? Web browser session. Supposedly that should be in one transaction, right? So this is a non-repeatable read. You see what I'm saying? Okay, but this is okay. This is okay because for a library system, this transaction is non-critical, right? So even if it's not serializable, even if it's not serializable, that's fine. Okay, even if some anomalies like this happen, users can tolerate it, right? So it's not necessary to enforce a very strong, very high, very aggressive isolation level. For what reason? You want to ensure that more people can access the database at the same time. Okay, so in fact, this recommitted level is so important that this is actually the default isolation level at Oracle and also at Postgres. Okay, so this is something that could be surprising to you, right? Because for someone new to transactions, right? He or she would imagine all these anomalies are bad, right? But as I said, sometimes you may choose to allow some of these anomalies because if you forbid all of them, and then the concurrency level is going to go down dramatically. Okay. So finally, there's one isolation level. This is a bad isolation level, right? You can basically, this exists only because, theoretically speaking, you could do this, but in reality, nobody will do this, right? Because this dirty read is very, very toxic. You see what I mean? Very harmful. All right, database systems do not allow dirty reads because this basically violates the all or nothing requirement of transactions. Okay. All right, now finally, let's talk about phantom, right? So I said phantom is something isolated, right? So this is like a patch. It does not appear formally in the definition of all these isolation levels. However, this is like a patch, all right? So the convention, so now here I'll be speaking about convention. The convention says, phantoms should not exist at the serializable level, all right? So serializable level should be the cleanest, and you can take for granted that the effect is always as if the transactions were executed serially according to some order. Okay, so phantoms cannot exist. Okay, but phantom can exist. At all the other levels. All right. So this is about the isolation level. All right. All right, guys. Before we end today's lecture, I would like to solicit some feedback from you. If all these things are clear to you, give me some feedback, please. Okay, awesome. Okay, all right, great. All right, so this is the end of today's lecture. I hope you have enjoyed it. So we will take a 2-minute break, and then we will start the tutorial. Okay, you don't have to leave. I will just keep the meeting session active, alive. Okay. All right. So I'll talk to you in a little bit. Okay.